Hey guys, the last time we spoke, I gave you this to do, and I took the liberty of just showing you the answer. Uh, First, recognize the fact that this is an aldehyde, so your longest chain must include the aldehyde. Um, I guess it's a 9-carbon aldehyde. Okay. And we're seeing the fact that these are all side groups, right? So what we have here is a ether side group we just learned because of the COC configuration here. So as an ether, we name this, of course, ethoxy. Here's another ether. Okay, this will be an isopropoxy. And then we have fluoro, we have keto, and then we end up with uraldehyde. So we give them their number like 4-ethoxy, 8-fluoro, 5-keto, 6-isopropoxy, and non-anal. That's not exactly correct. Okay, so you have non. You gotta indicate those triple bond, right? So you have 2-ine, you have 7-ene-al. Now the question is, do you have to write 1-al? Do you think 1 is necessary? Of course, in this case, 1 is not necessary, unless you have a dial. Okay, now, so that's the name, and I guess that's something that I want to take up with you the last time, from the question I gave you last time. So today we're gonna move on to more reactions. Let's clear this page, and let's take a look at another reaction. So today's lesson is reaction of carbonyl. Now this is going to be a 2-part video. Okay, first today we're going to look at aldehyde and ketone, and tomorrow we're going to look at carboxyl. Carboxyl is going to be interesting. Carboxyl is going to be there's more, let's say. Okay, for carbonyl, not so much. Now, actually, you know what? On a side note, before we look at the reaction of carbonyl, let's do some analysis of property, because we haven't been doing that. And let me just give you a little statistics, let's say. So I have some alcohol and some aldehyde. So I have ethanol and I have ethanal. Okay, and I have propanol and I have propanal. And I have propanone. Okay, I have butanol and I have butanal and I have butanone. Okay, let me just draw these while I'm at it too. So this is ethanol. This is ethanol. This is propanol. This is propanal. And this is propanone. Okay, let me quickly just show you butanol, butanal, and butanone. Now, what I want to stress about this, of course, is not their structure, because we already know their structure, man. We're so good at this, it's not even funny. A lot of you did very, very well on the tests in terms of naming these guys. You know, I'm quite impressed. You're doing a way better job than I am. All right, what I'm looking at here is boiling point. Okay, that's the property I want to look at, boiling point. Now, remember what boiling point was back in November. We talked about intermolecular force, right? And the boiling point is the breakage of hydrogen bonds, van der Waals, London dispersion force, dipole. Basically, whenever you have intermolecular force between molecule. So let's say, for example, ethanol, intermolecular forcing with another ethanol, there's a boiling point. Why? Because in order to boil ethanol, those intermolecular forces must be broken. And intermolecular forces, in terms of strength, is based on polarity. We remember that. Things are polar, like alcohol. Alcohol is polar because this is slightly negative, the hydrogen is slightly positive. That's a polar molecule. Okay, the boiling point is going to be higher because the strength of these forming hydrogen bond with water or whatever is going to be stronger. So it makes sense that you need a higher temperature to boil them. So let me give you some statistics here. Okay, ethanol requires 78 degree worth of heat to boil. So it takes 78 degree worth of heat to break the hydrogen bonding between ethanols. Okay, what about ethanol? Now you ask yourself a question. Which one is more polar? Okay, ethanol or ethanol? Is this polar? Is this that much polar versus OH? Now remember, difference electronegativity will tell you these things. OH has a pretty big difference in electronegativity. The delta En there is pretty high if you think about it, if you remember. Okay, remember O was 3.5, H is 2.1, and you take the difference. That tells you, of course, how polar something is. Well, you can do the same calculation with CNHs or CNOs. Would that be polar or very polar? And your answer would be no. Okay, ethanol is not very polar. It's polar. CNOs are polar. CNH is polar, but it's not that polar. Because it's not that polar, the boiling point here is going to be less. In fact, it's a lot less. Okay, so you're going from 78 degrees to 21 degrees. Okay, both of these guys are 2-carbon organic compound, of course, 2 different functional group. Because of the OH, that increases the boiling point actually a whole lot than C double bond O's. Okay, now let's continue. Okay, what about propanol? Let's compare ethanol and propanol. What's the difference between ethanol and propanol? Well, chain length. There's more carbon in propanol. Not a lot more, but 1 carbon more, but that's more. What happens when you increase chain length? Well, guess what? By increasing chain length, boiling point increases as well. So you went from 78 all the way to 97. Now that's not surprising. Okay, that has something to do with the hydrocarbon. Okay, the more hydrocarbon there is, the more chances of London dispersion forces. Okay, because you get to agree that this part is nonpolar. By having a lot of these propanol together, you are creating a lot of these nonpolar interaction. So on top of the polar interaction, you're actually getting more nonpolar interaction. Hence, more hydrogen bond, more intermolecular forces to break. Therefore, it only makes sense that the boiling point is higher, right? Okay, so let's do a little summary here. The increasing of chain length will increase the boiling point because of more London dispersion force. The more polar, the higher the boiling point as well, okay, due to the increase of strength of hydrogen bond. Hopefully, you guys are okay with that. Now, what about propanol? What would the statistic for propanol? Well, propanol is longer than ethanol. So, as I said, increase in carbon length, increase in boiling point. You're looking at 49 degrees Celsius. Okay, now, these are real statistics. I did not grab this out of my, statistics. So, it's 49 degrees. Now, obviously propanol is not going to be over 78 degrees, that's for sure, because polarity always overrides everything, okay, even chain length. All right, what about the ketone? We have a ketone right here. We haven't seen a ketone. What about ketone? Now, for ketone, you're actually looking at an increase compared to aldehyde. Okay, you have a 56 degrees Celsius for ketone. Now, the reason is quite simple actually. It's not that difficult. You can see that these two are very similar. Propanone is just slightly above propanal. The reason is you still have this, I guess, polarity here, the C double bond O. But the difference here is that for propanone, there's two sites of London dispersion force on the left and on the right. Whereas propanal only have this set right here. This is really nothing. Okay, there's not much going on here. But this is a whole lot. Since there's only one side to London dispersion force with, the boiling point will be lower than having two sides, even though the two sides are shorter. Okay, so having more sides overrides having less sides, I guess, even though you have a longer chain length. All right, so hopefully you're able to predict what this is. Okay, so you have butanol, which is longer than propanol, way longer than ethanol. So what would be the boiling point for butanol? Now, I'm not looking for a certain number. Okay, that would be ridiculous. I'm looking for bigger than who? As you can see, it's going to be bigger than that number. So the real statistic here is that butanol requires more than water, actually. It's 118 degrees Celsius for it to boil. So butanol, 4-carbon alcohol, takes more energy to boil than water. Pretty sick, huh? Butanol is 75 degrees. That's not surprising because propanol was 49 degrees. So that has to go up. Okay, we know the fact that butanone is going to be above butanal. It's not going to be much. You're looking at 5 degrees. And of course, you're comparing it to his brother, propanone. Okay, it's higher, of course, because not only are you getting, of course, more carbon chain, okay, more London dispersion force, but you're looking at longer dispersion force. I think that's what I said. So here's a little bit of property here that I just kind of want to go with you. We haven't been talking about properties. I really want you to know some of these things. I got to let you know, okay, there is going to be one more test for this course. And I'm going to ask you questions about this. Trust me, I will. So the idea I want you to have here is this, okay? Increase in chain length, increase in boiling point. Increase in polarity, increase in boiling point. Okay? Got it? Increase the amount of London dispersion force site or even hydrogen bonding site. Again, increases the boiling point. Now, these are not things that you don't already know. We kind of talked about them back in November, but November was a long time ago when things were normal. Except for me. Of course, never normal. All right, so let's clear this off and let's go back to looking at reactions because that's what we're here to do. Okay, so let's clear this off. Hopefully you wrote all of this down on a piece of paper. I hope you've been writing these things down on a piece of paper because I think it's better to write them down than just keep watching them, right? So the reaction here is called oxidation. Wow, doesn't that sound familiar? Okay. Well, we kind of looked at oxidation back in topic 9. Okay, but when we looked at oxidation back in topic 9, we weren't so concerned about oxygen, weren't we? We were more concerned about electrons. When we lose electron, okay, on a chemical reaction, if before and after is a loss of electron, so when you went from, I don't know, -4 to -2, that's a loss of electron. Or +2 to +6, that's a loss of electron again. We would call that oxidation. But today, we're not looking at electrons. You don't want to go back and look at electrons, do you? We're looking at gaining of oxygen. And there's quite a bit of scenarios. Okay, so let's take a look at example 1. Example 1, it consists of a primary alcohol. Okay. If you oxidize a primary alcohol, now take a look at what I have here. This is not a chemical. It is a chemical, but it's more like a symbol. It's a representation of a certain chemical. This represents oxidizing agent. Now, do you remember what oxidizing agent means? That means this thing has the ability to make this oxidize. Now, I'm going to give you 3 examples here that you might have to memorize. These are all oxidizing agents used widely in most chemical laboratories. The simplest one is hydrogen peroxide because that's easily accessible. We have K2CO2, potassium dichromate. And we have potassium permanganate. Okay, these are all popular oxidizing agents that you'll see very quite accessible in most laboratory. Even ours, we have lots of potassium permanganate. Okay, we have lots of hydrogen peroxide. Potassium dichromate, not so much. But let's just say, this is the reaction. You take a primary alcohol and you put it into an oxidizing agent. What are you going to get? Guess what? You're actually going to get an aldehyde plus water. Okay? Plus water. So it's pretty cool stuff if you think about it. And let's take a look at an example, an actual example. Let's take a look at my favorite alcohol of all time, ethanol. So if you were to oxidize an ethanol, let me draw this actually. Let me draw this. Because other than memorizing these reactions, I want you to understand these reactions. Here it is. Okay? Here's ethanol. And here's an oxidizing agent. Ethanol is going to turn into an aldehyde. The question is, how does it turn into an aldehyde? Well, the idea here is very simple. Okay? Basically, this H and this H will go away. All right? Let's write that down. This H and this H will go away. Now, it could be this H2. Okay? But it has to be this one and this one. These two are going to go. Because by going and hooking up with an oxygen from the oxidizing agent, this C will be missing a bond. Because he's missing a bond, he will decide to, I'm going to double bond with this oxygen. Okay? That's how it works. So what you're going to have here is this. Okay? Which of course is ethanol plus water. Okay? These two H is going to somehow grab an O from the oxidizing agent. This carbon right here, missing a bond, wouldn't mind, of course, bonding with the oxygen, creating an aldehyde configuration. Right? So that's primary alcohol. That's what primary alcohol do. Now, we all heard of other type of alcohol, like a secondary alcohol. What would a secondary alcohol do? Would a secondary alcohol also make an aldehyde? Well, it doesn't. I can tell you right now that a secondary alcohol makes a ketone. Okay, so let's take a look at a secondary alcohol. The simplest secondary alcohol, of course, is isopropanol. This is your simplest secondary alcohol. Okay, you can call it 2-propanol, isopropanol. No big deal. Let's call it 2-propanol today. Okay, and you are putting this into an oxidizing agent where this guy is gonna get oxidized. Okay, now by means of oxidation, we're not adding oxygen to this, but instead we're taking away hydrogen. So taking away hydrogen is also a way of oxidizing, if you remember from back in chapter 9. How are we gonna, which hydrogen are we gonna take away? Pretty obvious. We're gonna take away this hydrogen and we're gonna take away this hydrogen. Okay, they're gonna somehow pick up an oxygen here to give you this. Okay, now you know this is not complete because this C is missing a bond. This O is missing a bond. Oh, whoa, you want a bond? You want a bond? No big deal, let's bond together. There you go. Isn't that a ketone? So what we have here, of course, is propanol. That's water. Okay. So you have a primary alcohol oxidizing to give you aldehyde. You have a secondary alcohol oxidizing to give you ketone. Whoa. What about a tertiary alcohol? What would a tertiary alcohol give you? Well, let's take a look. Okay, let's take a look. Why not? Here's a tertiary alcohol, terbutanol. Or you can call it 2-methyl-2-propanol. So if you were to oxidize this with an oxidizing agent, okay, I have a problem. This is a huge problem. This H is going to go. Now, if you notice which H goes, you'll notice a pattern here on this one and this one. It's always the H that's connected to the O that's going. And it's always this H that is connected to the C that is connected to the O that is going. Right? The carbon that is connected to the alcohol here, this H or this H, these go. So look at this one. Look at this. This is the C that is connected to the alcohol. It has an H. He has to go. The C. He has two H's. One of them has to go. Take a look at this. He's saying to himself, I don't have an H. Well, there's an H right here with the O, but I don't have an H. I don't have an H like this guy. I don't have an H like this guy. I don't have any H's. I'm connected to 3 C's because I'm a tertiary alcohol, duh. So, I don't know how am I going to make water. This guy's saying, oh, I have an oxygen here, come and get it. But he's saying, oh, I have one hydrogen, but I'm missing one more. He's going to say, well, that's too bad. I ain't oxidizing you. A tertiary alcohol will never ever oxidize. Don't be fooled. Okay? So whenever you see a reaction and it's a tertiary alcohol you're trying to oxidize, make sure you tell the person who's asking you that question, hey, that's impossible because I can't find another hydrogen to make water with. Make sure you let them know. Okay? All right, so that's oxidation of alcohol. Obviously, by oxidizing alcohol, you get these carbonyl, like aldehyde, and ketone. So that's preparation of alcohol. Let's take a look at the reaction of alcohol, which is not interesting at all, because what we're looking at here is nothing more than a reverse of what we just did. So number 2, this is another hydrogenation reaction, a hydrogenation of ketone and aldehyde. Okay, so let's take a look at an example. So we have here ethanol. Okay, well, let's look at a general reaction here. Oh, no, that's fine. Okay, ethanol. Okay, if you react ethanol with hydrogen gas, with some heat involved, you're gonna get ethanol. Okay, so it's sort of like the reverse of oxidation, but it's not a reverse. It's not, because you're not taking ethanol and you're not reacting with water to get ethanol. So it's not a complete backward of what we saw with example 1. This is different. This is hydrogenation. Okay? There's no reducing agent here. All you need is a little bit of heat. Okay? When I say a little bit of heat, I'm really talking about anything higher than SATP. Okay? Anything higher SATP. Now, there's no specification in terms of what, because every aldehyde is going to be different. All they'd ask you to know is that you won't jump start this reaction unless it's above SATP. All right? So ethanol reacting with hydrogen gas in the presence of heat will give you an alcohol. So let's write that down as a general reaction. So you have an aldehyde, okay, reacting with hydrogen gas in the presence of heat will give back your alcohol. Okay. So does that mean a ketone works too? So if I take a ketone and I react it with hydrogen gas in the presence of heat, would I also get back an alcohol? Absolutely. Okay. Now, just to be precise, the alcohol that you're getting from an aldehyde is going to be a primary alcohol. The alcohol that you're getting from a ketone is going to be a secondary alcohol. So we have propanol reacting with hydrogen gas will give you 2-propanol. Okay, let me just draw this for you guys and then we'll call it for the day. So I have here ethanol. Okay, if you take 2 hydrogen, and of course you would put 1 hydrogen here and 1 hydrogen here, you will have exactly what I say you're gonna have. You're gonna have a primary alcohol. Here's your ethanol. Okay, so if you take your propanol, okay, and you react it with hydrogen gas, just like what we saw before. One of the H would come over here, one of the H would come over here. Okay, this will give you this, which is your 2-propanol. 2-propanol, isopropanol. All right? Okay, so that's pretty much the reaction of carbonyl. So the summary here is very simple. Just write a little summary. Okay, that primary alcohol oxidizes to give you an aldehyde. Okay, and vice versa. And second aldehyde alcohol will give you a ketone. And of course, vice versa. Okay. All right. Hopefully you guys are okay with this. Tomorrow we'll look at part 2 of carbonyl reaction called in the form of carboxyl. Now that's going to be a big deal because like we saw with alcohol reacting with alcohol giving you an ether, which is a new functional group with its own naming system, you're going to see that again with carboxylic acid. We're going to take carboxyl and we're going to react with alcohol to give you something called ester. Okay, and there's going to be some, I guess, biology lesson again tomorrow. And you know how good I am with that, right? That's pretty horrible. All right, so I'll see you guys tomorrow. Bye.